Hello and welcome to the web series ZeroPM Pieces. My name is Sarah Hale and I'm the project coordinator of a really exciting new research project called ZeroPM. In ZeroPM we are going to interlink prevention, prioritisation and removal strategies to protect human health and the environment from persistent and mobile substances. In the ZeroPM Pieces, the researchers in the project will tell you about one piece of the ZeroPM puzzle that they're working on. So without further ado, here comes a ZeroPM piece.
Hello, my name is Hans Peter Arp. I work for the Norwegian Geotechnical Institute and also the Norwegian University of Science and Technology, and I am the Deputy Coordinator of ZeroPM. So in this premiere episode, the first piece we're going to present of the ZeroPM puzzle is substance mobility. Now on the screen, I have a picture of me giving water to my son, and I'm doing so knowing a troubling statistic that we are hearing from drinking water producers all over Europe and in other countries. And that is that they are finding these very difficult to remediate persistent and mobile chemicals in their water, and this is an increasing problem. So on this graph, you see these purple dots with black in the middle. The purple dots indicate the size of the number of persistent and mobile substances that have been monitored each year in a Dutch drinking water source. And it's been increasing. And these black parts in the middle are if they exceeded a concentration that they find troubling for their water consumers because they could pose a health threat. And so this water company has been investing more and more into remediation costs, and that's been increasing. And it's a big issue, who will pay for this and what substances actually will break through to my son's water bottle. How did those chemicals get there? Now, chemicals are used all over society. Most of them are making our lives much better. But during synthesis and their uses, some of them were or could be transported into the environment. And once they're in the environment, they could, through various pathways such as rivers or groundwater, end up in a water treatment production facility. And if it gets through that water treatment production facility, like I showed you in the previous slide, it could end up in my son's water bottle. What are the properties of such a substance that can go through such a journey? Well, they have to be persistent and they have to be mobile. They have to live long enough in the environment, i.e. be persistent to survive the duration of the journey, and they actually have to be transported. And that's what we mean by mobile. In addition, we can also look at their toxic, and then that's a real concern. So on this slide, I'm showing another depiction of how this happens. So we have an industry over here that has some emissions from its factory, and it enters the groundwater and it makes what we call a plume. And what you find is the most mobile substances will be at the head of this plume and the least mobile substances back. So the most mobile ones will end up in, for instance, this drinking water well. Now in the 80s, a fellow by the name of Gustafsson, he wanted to characterize these chemicals better that will be ending up in this drinking water well, for instance. And so what he did was he plotted two properties. One is the soil half-life. In other words, if you put this chemical in the soil, how long will it take before it disappears completely, and what is the half-time of that? So he plotted this property versus something called the soil organic carbon partition coefficient, or KOC. Now, what that describes is basically how sticky that chemical is to the soil. I shouldn't call it sticky, I should call it sorption. How strong does that absorb to the soil? So the less the sorption to the soil, described by the KOC, the higher the persistency, the higher the chance it's going to end up in that groundwater. I should present some more details about what I mean by the KOC. So if you want to visualize how we measure a KOC, or the sorption coefficient, you can imagine a very simple experiment that actually you could do at home. So take a bottle, any type of bottle that you can close the top of, put some soil in the bottom, add a chemical, and then just shake it up. And then eventually those chemicals will distribute in the water and the soil phase, and the concentration will become constant at a certain time point. Then what you have to do next is you measure the concentration in the water. That you can't do at home, you have to go to a lab, but you take the water concentration and you take the soil concentration and you find the ratio. So we put the soil concentration on the top of the equation and the water concentration on the bottom. So the higher this ratio is, the more sticky the contaminant is to the soil and the less mobile. Also, the lower this value is, that means most of the chemicals are in the water, so it will be quite mobile. And you can do this experiment with soil, sediment, or sludge. So that's kind of explained science. Next thing is, how do we make that into a formal regulatory definition? Well, the German Environment Agency has developed such a regulatory definition for what they're calling persistent, mobile, and toxic, or PMT substances, and very persistent and very mobile substances. So how do you check if a substance is PMT or vPvM? Is first, in Europe, for instance, in the REACH regulation, if you're importing a substance or producing a substance that contains an organic chemical over a certain tonnage, you're supposed to evaluate if it's persistent. And if it is persistent, for instance, with the soil half-life, then you're supposed to say if it's mobile with the KOC. And in certain cases, you might exceed thresholds that would make the substance be called very persistent and very mobile. Or it's just persistent mobile. In many cases, it won't be a persistent mobile substance, so you don't have to do any further evaluation. But if it is persistent and mobile, or very persistent, very mobile, you have to look at toxicity, and then some of those could actually be a persistent, mobile, and toxic substance. So to go more into detail about where they put these thresholds, you see there is also a half-life threshold for soil, similar to that previous slide where I showed you the Gustafson chart. So that's there, and it's 120 days for persistent and 180 days for very persistent. But also in this criteria, you can look at other environmental media, such as water, which is obvious. If the substance is persistent in water, it's also persistent, but also sediments, because in many cases, a contaminant can enter a river, go through the sediment at the bottom of the river, and also in that way enter a drinking water well. And for the mobility, this is based on that KOC parameter I described earlier. And the German Environmental Agency set the criteria as less than a log KOC of less than 4.0, which is 10,000, as mobile, and 1,000, or a log KOC of less than 3.0, as very mobile. Currently, this is being discussed in Europe for implementation in more European regulations. And right now, they're talking about moving the log KOC to slightly smaller values. And there's some debate about that. So it'll be interesting to see in a year or two time, what are the KOC definitions we'll see in different European regulations. So there's also various rationale for this criteria. What's this debate happening? One reason why this debate is happening is here's a plot, as I call a histogram, of the number of substances that have been observed in drinking water. And this is different log KOC values at the bottom. So depending on where you put that cutoff for mobile and very mobile, you're giving kind of free pass for some drinking water contaminants to escape this definition. So that's the crux of the debate. But there's different rationales for also setting them where they are. Similar definitions can be found in other guidelines or regulations, such as in the Groundwater Common Implementation Strategy Working Group. There's also a similar regulation for biocides in Europe. They set a value at 2.7, and there's also various categories by the United Nations Food and Agricultural Organization. So this will be interesting to follow for me personally. And there's also a modeling way you can solve this, where to put the threshold. But one thing that also is coming up, which is also interesting, is that for ionic compounds, and many of the substances we look at are ionic, when you measure their KOC, they have huge variability, and there's various reasons for that, which I could point you to this paper that I have on the screen, but I'll just say there's huge variability. So how do we deal with that? And the approach that we're recommending is to look at that variability of measured data and taking a minimum value or some kind of statistical definition of where you want to set that log KOC for ionic compounds. This is the most practical way forward. Okay, so, but basically I'm just going to end with this, that PMT and vPvM substances will be on the move in the environment if they're let loose and could appear in your drinking water. So that's why in ZeroPM, we're making strategies to make sure we can contain them as best we can. Okay, so that's the end of the first ZeroPM puzzle piece on mobility. And I want to thank you for your attention and to all my great colleagues at ZeroPM. And don't forget to check out our website at zeropm.eu. Thank you very much.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.